Hello, I'm Mingqi Han, and this is the video explanation for homework 10, question number 1. In this question, we are asked to find out in lecture notes the definition and the simple properties, including the probability mass or density, mean, and autocorrelation function of these 7 processes, and explain the understanding of this process. So let's start with the first one. The first one asks about Poisson process, which is found over right about here. Wait, here, yes. So here, the definition of the Poisson process, or let's say the PMF, or the density function, is like this. So in this case, we have a t right here, but we can write it as t1 minus t2. Write it this way. So t1 xe1 and minus xe2 is a number of number or what a Poisson process defines in here. So yeah, this is the PMF. Sorry, then I think the density function, and here is the expected value. And to calculate that, here is how we calculate it. And of course, by instance, is that the longer the t time it takes, the larger the value it is. So it's basically just lambda, a constant that defines how rapidly that this value change, and the t, how long the time has passed. And autocorrelation is the autocorrelation is found over here for Poisson process. And for Poisson increments, this is the definition. It's just calculating the amount of increment in Poisson process, which over the time or over the period of epsilon. So we have an epsilon here. And by calculating this, or let's say the distribution function or the density function would be like this. Yeah, it's right over here. And because we're trying to calculate the amount of increments, not the amount of total value. So the amount of increment in the Poisson process should be always the same. So the increment will be lambda. It's a constant. It defines how fast it increments, but once it's defined, it stays the same. And for calculating the autocorrelation, so if t1 minus t2 is larger than the epsilon, the standard time is is lambda squared, and if it is smaller, it's this equation over here. The next one will be Poisson impulse. It's defined like so, and its expected value is also a lambda, because it's trying to calculate the impulse is similar to increment, but in this case, it's just the graphics look like this. It's just each impulses. And I believe here we have the autocorrelation calculated in this way. And the fourth one is semi-random telegraph signal. Let's say just starting with the telegraph signal. It's just the graph looks like this. It's just consists of ones and zeros at some given time or some given time period. And for a simple telegraph signal or semi-random, let's say that the difference between semi-random and random telegraph, because the next one is random telegraph. Semi-random is that a fixed one is at location x0, and the random one is not defined. It's either 1 or -1. So let's start with semi-random. Here is its definition, and the probability mass function is calculated this way. And here is what I had over here. But in this case, it's just for the first case when k is even. So it's equal to 1. The amount of, let's say, it's just the amount of ones. And the next one is when k is odd. And by doing so, it's just replacing this even as odd. And here, instead of 2, 4, something like that, we have 1, 3, 5, something like that. And it's also a hyperbolic function. It's sin sin SINH instead of cosh COSH, but the lambda t would remain the same. And the expected value here is 1 times the amount of where it equals to 1 and or where it is equal to -1 plus here. So it's basically just this equation, and we have this value right over here. And the autocorrelation is this function right over here, calculated in this way. And the next one would be the random telegraph signal. Remember that random is just the semi-random without the fixing initial 1. So at this point, it could be here, could be here. And so to define it, it's just having a extra constant. It's like flipping the semi-random with a probability of 1/2. It's just 1/2 probability of flipping that fixed 1 at a fixed 0 at a fixed 1 at 0, or once it's flipped, it's fixed -1 at 0, but each one has half the probability. So in this case, when we try to calculate the expected value, it's basically just the expected value of the semi-random with the expected value of that A, which is 0. So the entire thing is 0. And the autocorrelation should be the same as the semi-random telegraph signal. And the next one will be the random walk, which is defined right over here. I forgot to write this part down, but this x and t is this function. And so the probability mass function would be like so. It's just counting the amount of let's say ones increments or h has, and minus the amount of tails, negative ones, and we have the probability mass function. It's just counting them all together. And so it's written like this. Yeah, written like this. And the next is to find the expected value. By intuition, we know that, let's say if we toss a coin, we get head, we +1, we get tail, and we get -1. Eventually, if there's enough amount of tries, the expected value is the same amount of heads and the same amount of tails, which is equal to the same amount of +1s and same amount of -1s. So the expected value would be 0. And to calculate the autocorrelation, we have this function here, which is pretty much explained with this part. And the expected the autocorrelation would be the minimum of n and m of delta squared. Delta is the sorry, S squared. Yes, the S squared, because S is what we define the move, or let's say here, in the example we used S, so this will be S. And the next one would be the Wiener process. Yep, right over here. And the definition is here. It's the density function would be look like this, right over here. And taking the derivative, we get this function, the small f. And also, just like the random walk, its expected value is 0. And here is how we calculate the autocorrelation. And that's everything for this question.